Bell states are the backbone of quantum entanglement, fundamental in quantum teleportation, superdense coding, and the very foundation of quantum mechanics. We start today's video in understanding this fundamental concept, and I welcome you to the 20th episode in Learning Quantum Mechanics on my channel Physics for Students, and my name is Kronecker. What I want you is to imagine that you and your friend have a pair of magic coins. So here is your coin and this is your friend's coin. Now these coins are special because they are always linked no matter how far they are located. Now you both flip the coin at the same time, even though they land randomly as heads or tails. You notice something strange. What you notice is that if your coin lands on head, your friend's coin also lands on head. And if your coin lands on tail, your friend's coin also lands on tail. It is as if the two coins are talking to each other, although they are millions of miles apart. For example, one can be on Earth and the other can be on Moon. Now, what is really happening out here? Now, these magic coins are the Bell states in quantum mechanics. So instead of heads and tails, we have quantum bits like qubits that can be either 0 or 1. Now, in Bell states, the two qubits are basically entangled with each other, meaning that their outcome is always linked. And if one qubit is measured as 0, the other qubit can be also be 0 or opposite way depending upon which state they are. And this happens almost instantly. I would say this happens instantly no matter how far they are apart. Now, why this is important? Because Bell states actually show how quantum particles behave differently, and they also give you the simplest form of the concept which is called as quantum entanglement. Now, it also leads to something which is called quantum teleportation, although the practical usage is still on the way. It actually is sending information instantly. It also leads to super dense coding, that means packing more information into fewer qubits. So testing quantum mechanics is like proving that nature is truly weird at very small scales. Now, this is what is called the Bell state. Now, if we really want to understand a kind of a concept on a very mathematical way, then there are certain definition of Bell states. Now, the basic definition tells that Bell states are a set of 4 maximally entangled 2-qubit states. Now hold on, if you don't understand why do we mean by maximally entangled, I will make you understand. But before that, look in these states what they look like. It looks like this, and here you can see there is a phi with a plus sign on the top. So you can imagine these states as I have shown you earlier, 2 people or 2 friends, and they are linked. For example, Alice and Bob, which holding a magic coin, and this can be in 4 different connections, or you can say telepathic connections. So what happens here is that when you get a plus sign, if Alice gets head, then Bob also gets head. If Alice gets 0, Bob will also get 0. So if Alice gets 1, Bob will also get 1. This is the fundamental first state of the maximally entangled Bell state 1. The second state shows something like this, where you can see now here is a minus sign. You can say that it is always opposite. If you're happy, then your friend will be sad. So if Alice gets heads, the Bob will also get tail. And if Alice gets 0, then Bob will also get 1. Here I have shown that Alice is getting 1 and Bob is getting 0. The third state, here you can see, although there is a negative sign, it is called random but matched. That means the outcome is although linked, but it is a mix of states rather than fixed agreement or opposition. The fourth state is random, but here it is opposite. That means like the previous one, but Alice and Bob always gets opposite results. So these are what are called maximally entangled 2-qubit states, and this is how they are written. Now we will come in exploring why we are calling it maximally entangled state. But before that, going into maximally entangled state actually takes us to this part of the video. What are the features of the Bell state? So once we have understood that it is related to quantum entanglement, one thing happening here, without any time loss instantly happens over there, and these are the 4 states which you have seen. Now, if you talk of the features of Bell states, then the first, if I take these 4 states as Bell state, then there are primarily 3 features. Number 1, it is called maximum entanglement. That means each Bell state represents the strongest form of maximum entanglement, quantum entanglement. Second is what is called orthonormality. That means the 4 states are mutually orthogonal, meaning that they can be serve as a basis for any 2-qubit quantum system or quantum state. And the third is non-locality. Bell states exhibit non-local correlations that violate Bell inequalities. We will look at demonstrating that quantum mechanics is incompatible with local hidden variable theories. We are going to explore this one by one, but before that, obviously you might have a question why it is maximal. Now, if you take the contrary, that is the opposite of maximum, then what it is, it should be minimal or partially entangled. So in a partially entangled state, the qubits may be, I would say, may be correlated somewhat, but it is not perfectly. And in a maximally entangled state, that is the Bell state, the qubits are in pure superposition where no information about the individual qubits exist, although the joint system matters. So the partial entanglement is, okay, fine. Let me show you what do we mean by that. So the basic meaning of maximum entanglement means that 2 quantum system, any 2 quantum qubits are, they can be strongly correlated as possible. Knowing everything about one tells you everything about the other, no matter how far they are located. So you can say, for example, if I take this part, then the maximum state, if one qubit measured 0, the other qubit has to be 0. So if they are maximally entangled, that means measuring one instant reveals the state of the other. No classical mechanics, like for example any phone call or message is exchanged, yet the outcomes is perfectly coordinated. In case of partial entanglement, it is coordinated, but not as strictly as this. So this gives you a clarity of the first characteristic of Bell state, which is called what is meant by maximum entanglement. That means they are absolutely no idea what this particle is doing with the other, but they are very well correlated so that the information is not lost and it is immediately transmitted. We come to the next feature of Bell state, which is called orthonormality. Now, ortho actually is a Greek term which actually means perpendicular. That means 2 directions at 90 degrees in space. And normal generally means that which has got a unit length. Or you can say the total probability is 1. So together, orthonormal means that the states are independent and properly scaled. Now, what does it mean in case of a Bell's theorem? Well, the 4 Bell states, as you can see on the screen, are 4 different independent directions in the 2-qubit world. You can think of something, although it would be wrong, but for imagination, you can think them as a basis describing any 2-qubit system, just the way you take X, Y, and Z axis that describe the positions or coordinates in a 3-dimensional space. So orthonormality actually leads to 2 important parts. For example, number 1, if you take 2 different Bell states and multiply them, then their inner product is 0. That means they are orthogonal or they are independent. Second thing which tells is that if you take the inner product of a state with itself, it is 1. That means it is perfectly or properly normalized. So now let us see a quick example of what do I mean by the inner product is 0, and second, what do we mean by the inner product of a state with itself it is 1. So orthogonality of different Bell states, I am taking 2 states or 2 states, this one psi and phi, and they are orthogonal if their inner product is 0, which means this one. Now, if I take an example of calculating, let us check if this plus and this are orthogonal to each other. So we do this and then we get this one. This one means superposition either in 0, 0 or 1, 1 state. And this one obviously means superposition either in 0, 1 and 1 or 1, 0 state and 1, 0 state. Now, if we take the inner product of these 2 parts, then what we get this, and once we expand this, we get this. It's just simple calculations of linear algebra. Since this state are basis states that automatically it follows that this would be 0, which follows that the whole sum becomes 0, and we have proved our point that the conclusion is that these states are orthogonal. As I told, the first characteristic should be orthogonal, that means it is 0. Now the second point comes is normalization of the same Bell states. So what we do is that we take a state which is normalized with itself is 1. So let us check if this is normalized. So we take this, we are taking the inner product, expanding this, it shows this. Since basis states satisfy again this one, so we get this one. So calculating this gets to 1. So that means it proves that this one is normalized. So from here we can now draw a conclusion that orthogonality we have proved that different Bell states have an inner product of 0, and normalization we have just seen that the inner product of it is actually 1. So from here, we have already proved the first and the second point, and then we have to prove the third point. What do we mean by non-locality in Bell states? Those who are aware about quantum physics, you already know what is non-locality, but it is worth noting that in classical physics, if particles are separated, their behavior should be independent, obviously, unless there is some hidden mechanism or connection. What Bell states tell is that it exhibits correlation that defy classical explanations. That means these correlations cannot be explained by any local hidden variable theory, a theory that assumes that particles already know their future measurement results, which Einstein called spooky action at a distance, his famous statement. So how do Bell states actually demonstrate non-locality? Let us look in that part first. Let us consider the Bell state, this one. And suppose there are two experimenters. Again, we take the beautiful Alice and Bob. So Alice and Bob are given 1 qubit each and they move far apart. If Alice measures her qubit and finds it in the space of a state of 0, immediately Bob's qubit immediately comes as 0. If Alice finds it as 1, Bob will also find it as 1. So the key takeaway from this kind of an experiment on non-locality, number one is that the qubits, remember, they were not predetermined to be 0 or 1. Number two is that the measurement instantly affects the other qubit no matter how far they are. So you can be here, your friend can be at Alpha Centauri, doesn't matter. And the third most important is that there is absolutely no classical explanation for this. That means there's no signal travels between them at the time of measurement, which would require faster than light communication. So this is what we try to understand by the key points. Now, this actually leads to another important part which requires a lot of explanation. However, we will just touch base in today's video, which is called Bell's theorem and Bell's inequalities. Now, Bell's theorem is basically, mathematically, it shows that if a quantum mechanics follows local realism, that means classical objects intuition, then certain inequalities must be satisfied. What are those inequalities? In real experiments, what we find is that these inequalities are violated, proving that quantum mechanics does not obey any local realism. We also know that Bell's inequalities are equations that sets limits on correlations in any local hidden variable theory. However, real quantum experiments consistently violate these limits, proving that quantum correlations are non-local. Famous experimenters and including Alan Aspect, who received the Nobel Prize, and recent loopholes free test have demonstrated these violations. So from here, what we understand is that Bell's theorem shows that quantum correlations, as seen in Bell states, cannot be explained by local hidden variables. It also implies that quantum system must be described by non-classical mechanics, and this actually sets stage for our next part of the video, that is understanding how quantum evolution and transformations are governed by what we call unitary matrices. So we will now look in what are unitary matrices and how they act on a 2-qubit system. Now you all know what is unitary matrices. You have already done linear algebra, so I am just trying to give you a very basic definition. Unitary matrices actually play a very important role in quantum mechanics, especially in the context of Bell states. Unitary matrices helps us to generate, number one, manipulate, number two, and transform entangled states while preserving the probability. So first of all, what is a unitary matrix? So if I take a unitary matrix U and we show this one. So here you can see that dagger part is a conjugate transpose of U. I is the identity matrix and it ensures the U preserves the norm of quantum states, meaning that the total probability remains 1 after evolution. Now, how can we construct the Bell states of using unitary matrices? That is important, because until we construct them, then unitary matrices just remains in the books for doing sums. So Bell states are typically created using unitary quantum gates. And particularly I have discussed this, which I am not going to do. One is the Hadamard gate and another is the C0 gate, or which we call controlled knot acting on 2 qubits, C0 gate. So the Bell states we know are this. And first of all, in order to generate this one, which I just highlighted right on the screen, this one, we start with a separable state 0, 0, and we apply the Hadamard H on the first qubit, which results in this. So after applying Hadamard matrix to 0, 0, it results in this. So we have first started this one. Now in order to generate this part, applying the C0 gate, so what we will do is that if the control qubit is this one, first part we have already done. So if the control qubit is this one, then nothing actually changes. So applying C0 gate with the first qubit, nothing changes. If the control qubit is 1, then the target qubit flips. That means this part transforms as this one. You see, all the 0 zeros are becoming 1 0. So it actually flips, the 1 0 becoming 1 1. Which is exactly this one, because you can see here the states are 0 0 and 1 1. So we have got this. Now the next part is that how do we use unitary matrix to represent this process? In order to do that, we take the general Hadamard matrix, this one, and we apply this to the C0 gate matrix, which is actually this one. And the full transformation of the matrix after transforming looks something like this. So here what happens is this, actually this is a tensor product which I have earlier explained. H with a cross sign, this is the tensor product on I, acts on the 2-qubit system, this one. So if you want to say that what does it mean in simple English, I would say apply the Hadamard gate to the first qubit and do nothing with the second qubit. This is what the mathematical signs actually mean. So here you can see that from here what we can see is that H is the Hadamard matrix acting on 1 qubit. I is the identity matrix, which we already know means no change in the qubit, and the cross sign with a circle around it. This is the tensor product that we apply these operations of a qubit 2-qubit system. Now, the question is that why this is important. First of all, this is often used in quantum computing to create entanglement when followed by a C0 gate. Number one, and in a way to extend single qubit system to multiple qubits. So this is the unitary matrices govern the evolution of quantum state. This is the single qubit, and then when we go to the multiple qubit system, we get this. So in quantum computing, as you now understand, the unitary matrices govern the evolution of quantum states, but when we move to a multi-qubit system, we need to apply unitary operations to each qubit independently. And in order to do that, we need some kind of a mathematical operator which is called a Kronecker product. Now this is where actually Kronecker product comes in. It allows us to mathematically represent a single qubit unitary gates and extend it to multiple qubit systems. And this is what is known as Kronecker product, and we are just going to look over what is a Kronecker product. Now, a Kronecker product is also known, as I told you, I was just telling, the tensor product, and it is a way, and it is denoted by this. You can say it is a way to generalize matrix multiplication in order to get a larger matrix system. So, for example, like multiple qubit system, etc., we need something much bigger. So it involves actually multiplying each element of the first matrix with the second one. So for example, for two matrices, say for example A of size m times n and B of size p times q, the Kronecker product, that means A times B, is a matrix of size mp times nq created where every element of aij of A is the matrix of B. Now these are all English, I understand. We are mathematical people, so let me give you a simple example. If this part A and B, then the Kronecker product will simply look like this, nothing more. I will just demonstrate you with another example. So if we get A as this one and B as this one, we get the Kronecker product as this: 1 times B, 2 times B. What do I mean? That 1 will be multiplied by 0, 2 will be multiplied by 5, 3 will be multiplied by 7, and 3 will be again multiplied by 6. And we get this one: 0, 5, 6, 7. So if you do the multiplication, then this part 2 will be multiplied by 0, 2 will be multiplied by 5, 2 will be multiplied by 6, and 2 will be multiplied by 7, and so on. I mean to say, this actually carries on and on and on. So this is how it is important. So if you do this kind of a Kronecker product, what we get the result something like this. So the importance are, quite a lot, because in quantum computing, we use this Kronecker product in order to create multiple qubit system, because in order to make the processor or the quantum computing much better, much faster, much higher, so we do this part. And also you will see that this actually creates entanglement, which helps us in securing communication, credit card usage, and a lot of other very practical usage are there. So this is why the Kronecker product and multiple qubit system and unitary matrices, all of them are important. So we can say that Kronecker product actually is a way to generalize matrix multiplication in order to create a larger system. Why? Because that larger system will lead to a multi-qubit system, and this multi-qubit system will create definitely a betterment to the society in terms of communication, help to prevent hacking, and many other things. But here when I say that it is a way to generalize matrix multiplication, what do I mean by that? Well, I would like to demonstrate generalization of matrix multiplication, how the Kronecker product helps in this part of the video. So to illustrate how the Kronecker product generalizes operations in quantum system, let us consider the Hadamard gate again applied to a single qubit and entered into 2 qubits. So H is applied to this one. And in a 2-qubit system, if you want to apply H to both qubits, then the Kronecker product would look something like this. So the Kronecker product works by multiplying each element of the first matrix with the second, which I have already demonstrated, and this would lead to something like this. Now, as you can see, this is a 4x4 matrix. So this new 4x4 matrix actually represents the Hadamard matrix, which is applied simultaneously. You can say it generalizes the matrix multiplication of the first matrix with the second and creates a better, longer 4x4 matrix, which can be used for qubit operation. So from here, what we can say is that the Kronecker product actually extends single qubit operations to multi-qubit system. And instead of designing a new matrix from scratch for 2-qubit system, if we use something like H times H or Hadamard times Hadamard, systematically it generalizes the transformation. Also, this method works very well with unitary operations, because we are applying the Pauli X gate, which I have discussed in my previous video. You can go and look in that. The Pauli X gate to the second qubit would be written as I with a circle, that is the tensor product of X. So this has got a profound influence, isn't it? It creates a lot of good systems, quantum entanglement, using superposition, securing data, communication, and most importantly, which I have not covered, which is called dense coding. That means you are actually storing a lot of information in a single space. That is why it is called dense coding. So now it is a time to get a quick summary of what we have learned today. First of all, what we have learned is regarding Bell states and entanglement. We have learned that Bell states are specially normal entangled 2-qubit, maximally entangled 2-qubit system. They exhibit non-locality, which means that measurements of 1-qubit system instantaneously affect the other. And we have seen the example of Alice measures 0 and Bob collapses to 0 as well. Then we have learned orthogonality and orthonormality. Bell states are mutually orthogonal, and we have shown that it shows 0 as well as 1, and we have demonstrated that by very simple mathematical example. We have also learned what are called unitary matrices. A unitary matrix preserves quantum information and ensures reversible transformations. Example, the Hadamard matrix, where unitary operations are essentials in quantum gates and circuits. We also learned about what is an important mathematical tool, Kronecker product or tensor product, and generalization. We learned that Kronecker product extends single qubit operations to multi-qubits operations. For example, Hadamard gate can be taken to 3 qubits also as h times h times h. The principal scales quantum operations efficiently. What we learned overall, now we can say that number one, Bell state showcased the power of quantum entanglement and non-locality. Unitary matrices govern the evolution of quantum states while maintaining probability, and the powerful Kronecker product generalizes the entire quantum operations to multi-qubit system. So this progression from Bell's theorem to practical quantum computation, revealing how fundamental principles shape the real quantum systems, and it is ultimately creating a lot of difference to computing and creating a positive impact to our society. So that's all for today's video. I would like to take time to thank you for watching this video. If you have liked, please do subscribe to the channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. And a quick information, very important two podcasts coming up on my other channel, General Relativity Explained. One is at today, which will be starting at 8 p.m. Indian Standard Time, and the other coming very soon. You can wait for the surprise. Thank you very much.